here shows how can you know that, or how can you show that magnesium oxide and sodium oxide are basic. Now, so this is something strange, okay? Because for sodium oxide, we can know that after they dissolve in water and then we measure the pH change will be okay. So here shows the chemical equation. After reacted, we form 2 sodium hydroxide, and of course the pH value will be greater than 7, right? But this seems not so good for magnesium oxide. Now here there is some amendment here, okay? It is no good to write down which is water insoluble. Instead, I would say it reacts slowly with water for MgO. Yes, they MgO actually will react with water to form MgOH2 with magnesium hydroxide, but the process is very slow. So if something react with water to form hydroxide, which is very slow, it is hard for us to make the comparison. It is not that the hydroxide ion seems don't have too much, then how can you prove that it is acidic or not? So the first statement is not a good answer. I would recommend the second one. This is 100% sure. No matter the reaction rate is fast or slow or even insoluble base, I can do the same job. Yes, in order to test something is alkaline or basic, the best method will be allow it to react with acid and measure the not pH, measure the change in pH. Okay, then if the substance, the metal oxide is really basic, then the pH value of the hydrochloric acid should increase because some hydrogen ion is gone. And here shows you 2 chemical equation. So just immersion, this is a kind of neutralization, is fine. All right? So please be careful. Don't use water. Instead, use the opposite chemicals. For point 2, let me skip first, okay? And let's come to point 3. Again, how can you know that all these non-metal oxides are acidic? Yes, so you got the answer, right? So you got the answer. The most straightforward one will be dissolve in water. And if the solution is less than 7 for the pH, then it's an acid, right? Now, here shows you 2 typical examples. The SO2, so if you study the chapter about acid rain, so you get the idea, this H2SO3. What about Cl2O? Yes, this is HOCl. This is the same species that when chlorine dissolve in water, disproportionation. But we need to balance the equation. Here is done. And for the P4O10, okay, let me tell you the answer first. They form phosphoric acid, and 6 water is needed to form 4 phosphoric acid. Now, I know that some of you are not happy with that. How can I draw the conclusion? Now, Here, I give you the hints. The hints is when you dissolve the non-metal oxide into water, the oxidation number of the non-metal remain unchanged. No change in oxidation number. And here shows. So always keep in mind this is okay. But the same problem rise again because silicon dioxide do not soluble in water. Again, how can you know that this is acidic? And now I'm sure you got the idea. For something that is water insoluble, what about dissolve it in sodium hydroxide? Well, if you dissolve it in sodium hydroxide, the pH value of the solution will drop because part of the hydroxide ion is consumed, right? So here I showed you the equation to form NaSiO3, Na2SiO3, and H2O. Yes, first of all, the oxidation number remain unchanged. The second one is, okay, some of you notice that the equation is not balanced, so we should have two sodium hydroxide. And in fact, they should be hot solution in order to complete the reaction. And for some of you, they will find that the equation is very difficult for you to memorize, right? I give you a reference, so please complete this one. CO2 dissolved in NaOH. So how can you write down the balance equation? CO2 is an acidic oxide, right? So I'm sure everyone can write down this. And we got 2 NaOH here. The sodium hydroxide can help to remove or absorb CO2 from air. So you can compare all these two equations. Both carbon and silicon belongs to group 4. So if you can write down the purple one, I'm sure you can write down the blue one because everything is the same. Right. So here is the non-metal part. So finally, so what about the missing part is, what about aluminum oxide? There is some terms that is new for you. It's called amphoteric. Yes. So that means they can act as an acid or as a base. Again, please keep in mind, this is insoluble. This is insoluble. So what should we do? Yes, we use hydroxide ion to prove it is acidic, and the pH value of the solution will drop. This one, do you still remember this species? This is the one formed when excess sodium hydroxide solution is added to the aluminium ion solution. White precipitate is formed, and then we dissolve to form a complex salt, and here is the complex salt. So in order to balance the equation, we need 2 hydroxide ion and 3 water. Help you to remind again, compare with aluminium ion solution react with excess hydroxide. So you can see after the aluminium oxide react with sodium hydroxide, the solution's pH drop. Well, that means aluminium oxide is acidic, right? What about if aluminium oxide react with HCl? Well, this is simple because that is metal oxide react with acid. So you learn this in grade 10. Yes, to form salt and water. Acid react with base to form salt and water only, and the coefficients are like this. So of course, the pH of the solution increase, right? So that means the aluminium oxide can serve as an basic or an acid. So for those students who are absent-minded, let me give you the equation again. Compressed iron. Okay, so you can expect this is most difficult part for aluminium oxide. Well, next one, please, and you can pause the video first. So let's back to the discussion. First of all, P4O10 can react with NaOH. Is it correct? Yes. Because it's an acidic oxide? Sure. So because this is an acidic oxide, that's why they can react. So the answer is A. Both statements are correct. But the second one is the explanation of the first one. Next, aluminium oxide soluble in water? No. Aluminium oxide is an amphoteric oxide? Yes. So the answer is easy. C. Question 36 in 2013. Both aluminium oxide and magnesium oxide behave similar in acidic or basic properties? I don't think so, because I never heard aluminium oxide is the same as magnesium one. Magnesium cannot be amphoteric, so I wonder, is it true or not? The second statement is both of them are ionic oxide. True. So again, the answer is C, because the first statement is not correct. Magnesium oxide is not amphoteric. Finally, what about the oxide added to water to give a acid? So easy, right? Because everyone knows that carbon dioxide dissolves to form carbonic acid. For B and C, they are not soluble. Sorry. Silicon dioxide is glass or sand. Of course, this is not soluble, right? Lithium oxide is a group 1 oxide. They will react to form hydroxide, just like sodium oxide. Next one, please finish 8 and 9. So here shows. I don't think this is difficult for you to draw the diagram, right? Sodium oxide, please pay attention, is an ionic compound, while the Cl2O is a molecule. And don't forget state behavior. So in 2015, so many students forget to write down their behavior and then lost marks. The Na2O form an alkaline solution, Cl2O form an acidic one. And 2016, there involved actually, there is a typo here. So it should be MgO is inserted, but it doesn't matter, okay? Doesn't matter. So you can add it afterward. So statement question A, which of them can conduct electricity in molten state? What that means is about ionic compound. Only ionic compound become conductor in aqueous state. So the answer is easy. Well, sodium oxide, aluminium oxide, and don't forget magnesium oxide. Okay, it doesn't matter because it's my fault, right? I forgot to put the MgO. So even part A, you don't get it, no problem for MgO. The second one is why silicon got the highest melting point among, hey, be careful, among the covalent oxide. Well, that means if the oxide is not covalent, you no need to discuss. Okay, now, so everyone knows silicon dioxide got giant covalent structure, level of covalent bond, blah, blah, blah. Okay, very good. This will be contribute 1 mark. But what about the second mark? The second mark is, what about other covalent oxide? What about P4O10? What about SO2? All right, the others are, exist as molecules that only contain weak van der Waals force. And for part C, so you can copy the equation from above. So I don't think this is very difficult for you. Next one, I would say this is a obvious and easy to understand topic is discuss about the atomic radius. And here, I try to introduce a new term for you. So across the period, they got same occupied electron shell. Yes, the DSE will take care of it. Occupied. And now we got the sharing effect. So allow me to introduce what is mean by sharing effect. Sorry, not sharing, shielding effect. Sorry, shielding effect. So let me introduce first. So imagine for the case of sodium. Now this is sodium nucleus which got 11 proton. Okay, and we got first shell which contain 2 electrons. The second shell we got a electron, and the third shell which only got 1 electron. Okay, so yes, there is attraction between the nucleus and the outermost shell, but don't forget, actually, the inner shell may block the way between the third shell and the nucleus. So from calculation, yes, there are altogether 11 protons, but the first shell will block 2 for you, while the second shell will block 8 for you. And finally, what you remain is 1 proton because the rest of them are blocked by shielding effect. Just imagine when you go to the cinema and the one who sits in front of you may block part of the screen, right? If the guy in front of you is very tall or very fat, actually your view may be blocked by him, but your friend on your left, on your right hand side, because all of you belongs to the same row, so they will not block you. So in this case, for sodium, the outermost shell electron experience only 1 proton attraction. In fact, this is what we call effective nuclear charge. Alright, so try to compare our study with chlorine. Chlorine don't have the iron. Instead, they got 17 proton inside. And again, for the first shell, 2 electrons. Second one, a electron. What about the third one? The third shell, we got 7. So, as I mentioned, the electron on the left or on the right will not do anything, right? In shielding. So, for each electron, what they experience is 10, not 10, but 7 protons. 7 protons. Yes, so you can see chlorine got stronger effective nuclear charge than sodium, and hence that's why the size of chlorine should be smaller than that of sodium, because in chlorine each electron will be held strongly, and that's why the size of atom decrease across the period, because when you move along the period, then the effective nuclear charge will increase. So this is the case when we move along the period, the size of atom decrease. So please maybe I think you should highlight this, okay? Now, the next one is, yes, now we learn a new word is called shielding effect. The reason behind is the proton increase. So the effective nuclear charge filled by the outermost shell is also increased. Well, this is something related to electronegativity with the same idea. Outermost shell will be pulled closer to nucleus and hence decrease the atomic radius. Next one is, what about down the group? Now, down the group, there are more occupied electron shell, but the actually the effective nuclear charge will decrease. So what's wrong? Okay, let's see. And here this time we use a new page. When we discuss down the group, I try to use potassium and sodium as illustration. Now, both of them got cation with single positive charge. Again, the first one 2 electron, the second shell a electron. But the difference is, for the potassium, I got a third shell, also 8 electron, and comes to the outermost shell, 1 electron. Right. For sodium ion, I got 11 proton. Potassium ion, I got 90 proton. Okay, so have a calculation. The effective nuclear charge for sodium is 11 minus 2 minus 8. This is inner shell. Well, finally, equals to 1, or positive 1, okay? But for the potassium, it's 19, again, minus 2, minus 8, minus 8. Again, these are inner shell. Finally, also positive 1. Well, both of them, the effective nuclear charge is the same, right? Both of them are positive 1. But don't forget, their distance are different. Potassium got 1 more filled electron shell, increase the distance between nucleus and the outermost shell electron. And so you can expect with the same attractive force, but potassium got longer distance. Of course, longer distance means weaker force, right? That's why the size of potassium is greater than that of sodium. Okay, let's back to our notes. Yes, sometimes we will say they experience less effective nuclear charge because for this purpose statement, we have considered the distance already. Okay, and that's why the relative, the atomic radius increase. So here, if you're happy with median, here shows you the illustration. So please feel free to have a look. All right, so this is the unit 41. So if you got any questions, please ask me. You are always welcome to do so. Okay, so see you next time. Bye-bye.